to get the lowest number out of that, what we have to do? We have to shift the binary point left. Okay. So you see, I have written in the green line that there will be many zeros, okay, prior to the number 1. Okay. So if you want to get the lowest number, smallest number in floating point, and we have to use 32-bit system, we use 7 bits in exponent. Okay. So 7 bit in exponents means 2 to the power 7 minus 1. This will be 127. So all 1, okay, all 1 in 7 bits, they are all ones. Okay. This all 1 represents numbers 127 in decimal. All 1 represents 7 bits represents number 127, and this sign represents minus 127. So that means there will be left shift of binary point by 127 digits. Okay, 127 digits. So your binary point by the value would be 0.000 up to 127 times, and then the remaining mantissa will be there. So this value comes to be 1 by 2 into 2 to the power minus 127. If you calculate this number, the magnitude of this number 0.000 up to 127th position, and then only one, then after that remaining 23 bits zeros, we will have this value equal to half into 2 to the power minus 127, or in decimal it is 0.3, because 2 to the power 10 is 1024. Okay, 2 to the power 10 is 1024. So from there it is actually 1 by 0.3 is coming. Okay, 1 by 1000 something will be there. Okay, and then 2 to the power minus 1, 2 to the power minus 10 is there. So that's why 1 by 1000. So that comes to be near about 0.3 into 10 to the power minus 38. This is the smallest number in floating point. Okay. Then similarly, for largest number in floating point is what? Is this that I have explained in the green line. So for largest number, sign bit is 0, we are considering positive number, and remaining 23 bits are all 1, that is the highest mantissa. Okay. Highest mantissa is possible is all bit are 1. Okay. So we keep all 23 bits 1. Then again sign bit is 0, because we want to shift the binary point. Okay. Right. Okay. Right, so that how many shifts will be there? Again 7 bits. 7 bits in decimal, it represents 127. Okay, 127. So that means your initial number is 0.111, all 23 bits. This here the binary point would be shifted by 127 decimal digits. The binary point would be shifted by this many digits, 127 digits. So your number would be 1111111, many ones. Okay, 127 ones. Then your number will be 23 bits 1. Okay, so in decimal it is coming to be this one. Okay. 1 point, this binary, it is 1 minus 2 to the power minus 23. Okay, because 23 bits is there, and here it is into 2 to the power 127. So this is the largest number. Is it clear?
Yes, sir.
Okay, so now we'll go to the topic quantization of filter coefficients. Just theoretical, it is only used for theoretical purpose. Okay, so basically what is written, it is clearly understood that for on a general purpose computer, the accuracy with which filter coefficients can be specified is limited by the word length of the computer or length of the register provided to store the coefficients. Since the coefficients used in implementing a given filter are not exact, the poles and zeros of the system function will, in general, be different from the desired poles and zeros. Okay? So you cannot implement the desired poles and zeros using the fixed storage computer system. Okay? So consequently, we obtain a filter having frequency response that is different from the frequency response of the filter with unquantized coefficients. So after quantization, obviously there will be quantization. Okay, quantization, you know that you choose some quantity, analog quantity, and you convert it into digital value. Okay, you have a whole range of analog value of filter coefficients. Then that filter coefficient should be converted to digital value. So due to that, quantization error will occur, okay, and the filter response will change if you convert that into binary values. Filter coefficients will change. So here the analysis is provided what should be the response. Now to illustrate the effect of quantization of the filter coefficients in a direct form realization of an IIR filter, let us consider general IIR filter with system function this. So we have today also we have seen that this is the IIR filter coefficients. Okay, Hz is equal. This is the ratio of numerator and denominator polynomial. Now, if you find the roots of numerator and denominator, you will get zeros and poles. Okay. Now, after quantization, okay, that means converting the analog value to digital value, this value will change, obviously, because we use the finite storage register. Okay. So here, uh, so let us say that coefficients have been changed from bk to bk bar, and the coefficients have been changed to ak to ak bar. Okay, after quantization. And also due to that, transfer function hz will change from hz to hz bar. Okay. Now, where the bk set of bk and set of ak bar are the quantized coefficients and can be related to the unquantized coefficient bk and ak by the relations ak bar is equal to ak plus delta ak and bk bar is equal to bk plus delta bk. So that tells that how much error is there, how much change is there in the two coefficients, that is before quantization or after quantization. So and this delta ak and delta bk represents what is the quantization errors. Okay, because that is the only error possible, that is half of LSB. Okay, quantization error. Now here we represent the denominator of AZ, okay, that is original transfer function, is given by this. Okay. So it represents the pole product, okay, that is 1 minus P1 Z inverse into 1 minus P2 Z inverse into 1 minus P3 Z inverse. There are different poles of that system. And in the similarly, if you quantize it, there will be the poles, okay, and denominator will change, so the poles will change because AK has been changed. Okay, AK has been changed to AK bar, okay, the filter coefficients. Similarly, here PK poles will be changed to PK bar. Okay, simple. It is as simple as that. So that means there is change in the values of poles after quantization. So new poles is what? PK bar is equal to PK plus delta PK. Okay. And there are n number of poles because order of this denominator is goes to k is equal to 0 to n. So poles will also go from 1 to n. Okay. And where what is delta pk? Delta pk is the error or perturbation resulting from the quantization of the filter coefficients. So delta pk is the perturbation error. Okay. It is called perturbation because once you force something on, we apply some process, and due to that, if something gets changed, that is called perturbation. So poles get changed due to the quantization, so that's why it is called perturbation error. Now we shall now relate the perturbation delta pk to the quantization error in the AK. So what is the relation between change of filter coefficient to the change in the pole of the system? Okay. So that can be calculated as delta pi, okay, is equal to sum of delta pi divided by dou pi dou ak into delta ak. So that means for an ith pole, okay, for an ith pole, the it will depend on the change in the corresponding value of pole. Ith pole will depend on not only on a particular coefficients, it will depend on all the filter coefficients. Okay, so there are n number of filter coefficients a1 to an. So we see that it is a summation of dou pi by dou ak into delta ak. So that represent what? That represent change of values of poles pi, okay, divided by change of values of coefficients ak, where k goes from 1 to n. So that means dou pi, say it ith pole, so it is dou pi by dou a1 into delta a1 plus dou pi by dou a2 into delta a2. Okay. So that means there is change in each filter coefficients ak, that is delta ak. So what is the change of a filter of a pole for each and individual filter coefficients? So it is not that magnitude of one pole will depend on magnitude of one coefficients. It will depend on all the filter coefficients. Okay. So this is given by delta pi or perturbation error. Okay. So there are two things. One is only error delta pk, and means change in the pole value, and perturbation error is delta pi. Okay, that comprises the change in all the change of the effect of change of poles due to the change in all the values of filter coefficients. Okay. Now here it is written that delta pi dou pi dou ak is the partial derivative of pi with respect to ak, represents the incremental change in the pole pi due to a change in the coefficient ak. Thus, the total error delta pi is expressed as a sum of the incremental errors due to changes in each of the coefficients ak. Okay. So the partial derivatives dou pi by dou ak can be obtained by differentiating dz with respect to each of the coefficient ak. So this value further can be calculated, dou pi by dou ak further can be calculated by differentiating dz with respect to filter coefficients. So let us do it this way, that dou dz of dou ak for at a particular value of z, that is equal to pole pi, is equal to dou dz by dou z into dou pi divided by dou ak. So at z is equal to pi. So this del z and dou z and dou pi will cancel out. Now then dou pi dou ak is what? Is equal to dou dz by dou ak at z is equal to pi. Okay. Similarly, dou ak means dou dz by dou z at z is equal to pi. So numerator of this equation is what? Numerator of this 7.6.8 is actually dou dz by dou ak at z is equal to pi is equal to z is equal z to the power minus k. Because if you see the polynomial, okay, of dz, so it is a partial derivative, so its coefficient is ak. Okay, so ak into z to the power minus k, ak into z to the power minus k. So you can see here that dz is equal to this one. Okay, so here dz is, if you differentiate dz with respect to ak, okay, then you will get z to the power minus k. Okay, z to the power minus k at z is equal to pi. So it will be equal to pi to the power minus k minus pi to the power minus k. This minus is due to differentiation. Okay. So we can write that denominator of 7.6.8 is equal to this one, dou dz is equal to, so they have differentiated it at z is equal to pi. So after this you will get this formula. Okay. So therefore 7.6.8 can be expressed as, that means this equation can be expressed as this way. Okay. this formula 7.6.11. Just go through this this derivation. Okay. So substituting of the result in 7.6.11 into 7.66, this equation, you will yields total perturbation error delta pi. So it is slightly critical formula, but here it is useful to understand the change in the values of poles or a particular pole. So this expression provides a measure of the sensitivity of the ith pole to changes in the coefficients AK. An analogous result can be obtained for the sensitivity of the zeros to errors in the parameters BK. Okay. So the terms Pi minus PL in the denominator represent vectors in the z plane from the poles PL to the Pi. If the poles are tightly clustered as they are in a narrowband filter, as illustrated in figure 7.36, the lengths Pi minus PL are small for the poles in the vicinity of Pi. These small lengths will contribute to large errors and hence a large perturbation error delta Pi results. So here you see that so there are poles of a bandpass filter which are closely related, closely pressed to each other. Okay. Then what happens? The difference in this term Pi minus PL, if it is small, then Pi minus PL is small. Okay. Means if the poles are very close to each other, then obviously this whole quantity delta Pi, okay, this is the ratio that if this difference becomes smaller, then the whole ratio will become larger. So perturbation error will be more. So it creates problem for a narrowband filter. Okay, and what happens in the narrowband filter is that poles are very much close to each other. Okay, because poles represents the resonance. Okay, and if the poles two frequencies are close to each other, that and if they are narrow band, okay, that means bandwidth for each poles is very small, and the difference, the separation between the two poles is also small. In that case, it will cause lot of error. Okay. So the error delta Pi can be minimized by maximizing the lengths Pi minus PL. This can be accomplished by realizing the high order filter with either single pole or double pole filter sections. Okay. So there will be many sections. Each sections will be of single pole or double pole. So and you have to constitute an higher order filter. Okay. So that way that effect can be minimized. Okay. So this is some analysis regarding the poles, the analysis of the quantization effect. Okay, so it has given some examples. You may go through these examples, but whatever the purpose of this topic, okay, that is clearly understood, that if you, and we have seen that the poles are affected a lot when the filter coefficients gets changed, and that occurs the due to the change in the due to the quantization. So this is the mathematical study we have analyzed, and some graphical analysis also there, but since it will go it will take a lot of time and beyond our scope of discussion. So I am not going into it detail. And if you find interest, then you can see it later, and you can ask me if you find any difficulties. So for with this, we finish the second module, and if you have anything in your mind, you can ask me now. Okay. So the topics that we have discussed till now for the second module, then you can discuss me now. Are you studying? Have you studying the second module? Because we have to arrange quiz for this module.
Sir, not the whole thing, sir, but I started studying the second module, sir. I'll do it in this week.
Okay. So anybody wants to tell anything?